Okay, so hello everybody. For today's lecture, you had a rough 1 week and a half. So today we are going to talk about some simpler things. So probably this can lighten up you a little bit, so that you will work. Like, there will be lots of problems in the contest, but they're not very hard. So today we will be talking about mathematics a little bit, about number theory and how we can implement it in algorithms. So the first question, the very short question, what is prime number? Do you know what prime number is? Okay, can you give me your definition possibly?
Divisible by itself or
It's
one.
only divisible by its own or one.
Like example by 3.
Okay, yeah, but can you give me a definition for that?
It can be divisible by its own or one.
Yeah, exactly. So it can be divisible by only one or itself. So the question, how we check that the number is prime? So any ideas? So we are given a number n, and you have to check that n is prime number. What will be your?
And modulo 1.
So like this seems like you want to check that it doesn't divisible by any other number before n, right? So you just go for I equals from 2 so n minus 1 if n is divisible by if n is divisible by I, then return false. Okay, so this is reasonable. We just go over all the possible divisors of n and check that none of them are divisible by n. Okay, any ideas on how we can improve this algorithm? Yeah. I mean, if you don't know yet, it can appear very tricky. So suppose that n is divisible by something, then it can be represented as multiplication of two different integers. The idea is that one of them are less than square root of n. Okay? So because if this one is bigger than square root of n and this one, bigger than square root of n, then the multiplication will be bigger than n. Right? So you multiply this one by this one, you get n. So this is not exactly what we want. Thus, one of them should be less than square root of n. So to check that the number is prime, we just have to go over all numbers from 2 to square root of n. Typically in like C-like languages, it is written something like that. For in I equals to 2I times I less than or equal to n, I plus plus. This is what it looks like typically. So you go from 2 to I times I less than n. This is the same as comparing the square root of n, right? So you just check there. You put in the square and compare with n. So you don't have to calculate this using doubles. You can do this in integers. So like you don't have any problems with precision and etc. Okay. Okay. An interesting additional question here. An interesting question. So, okay. Yeah, you can see. You want to find all the divisors of n. What are your? So right now we just check that this is prime number, so it doesn't divide by anything. But can we check in a similar manner on how we can find all the divisors of n? Like I will give you some moment to think. Probably someone in Zoom chat can tell me. So again, you can consider this one where n equals to p times q. Is that one of them are less than square root of n. So like this should give you an intuition as well to do that. No ideas, neither in Zoom nor here. Okay. Let me then explain it. So you just go for, so you could consider for p from 2 square root of n, if n is divisible by p, then we have two divisors at the same time. So one divisor is p, and another one is n divided by p. And that's it. So because every time when you have less than square root of n, you have the pair which is higher square root of n, which is n divided by p. So this is kind of how you find all the divisors of. So in this manner, you just find, like, for example, you could add it to the linked list, or like to array, to vector, and so on, and then you just get the list of all divisors of n. Okay. This is the brief start. So like we now understand how to check for prime number and how we find all the divisors. That's the good start. Now it becomes a little bit more complicated, a little bit trickier, but still simple algorithm. So you want to find the GCD of A and B. What is GCD? Is the greatest common divisor. So this is the largest number that divides both A and B. The algorithm is quite simple, so I will write it right now and then explain how it works. So if B equals 0, then return A, else return GCD of B and A. Here is the algorithm, just we pass two numbers. This is the first algorithm. If B is 0, then the answer is in A. Otherwise, we swap two arguments and divide, like take the modulo of A modulo B. Okay, why such a thing happens? So I have to explain to you a little bit of the Euclid algorithm and how to find it. So the idea is simple. It's like we take A and try to present it in this way. So it is pi times b and something modulo b. So this is the reminder. Okay, so suppose we want to find the GCD, which will be d usually. So you see that A is divided by d and b is divided by d. Okay, then Q1 is also divided by d. Then we take b and do the same trick, but already with the reminder. So it is again, it is divisible by d. We know that q1 is divisible by d because from here then q2 is also divisible by d. Then you just go, you just take q1, which is equal to p3 times q2 plus q3, and so on and so forth. The idea is that q is always decreasing. So it is always decreasing. So finally, at some point, you will have something like that. Qn equals Pn plus 2 times Qn plus 1 plus Qn plus 2. So at that point, at the very end, the remainder will be 0. Because it always decreases, decreases, decreases. At some moment, it will stop this operation. So yeah, so A bigger B, bigger Q1, bigger Q2, bigger. So finally, you will find this 0, and the answer then will be this one. I don't know. Oh, yes. Yeah, the answer will be this one. So as you can see, this is similarly here. If out of two numbers, the one is 0, then the other one is the answer. So we kind of, this checks that we went to the latest situation here. So when the remainder is 0. So if the remainder is 0, then the number is exactly as you want. Okay? And this is, as you can see, this is B and A modulo B because we always took the remainder here. So this is the whole algorithm. The idea behind that is that it works in logarithmic time, depending on their numbers. So it will work in log A plus log B. The proof is a little bit tricky, so you have to know what is Fibonacci numbers are. Do you know what Fibonacci numbers are? Yeah, Fibonacci numbers.
Natural or rational? Rational or natural?
Natural.
Natural. 0, 1, 2, 9.
Yeah, exactly. So like their Fn is equals Fn minus 1 plus Fn minus 2. That's the recurrence relation, right?
Yeah.
So you kind of know this. Okay, good. The idea is that you can prove that at each moment B is less than Fi. So it always becomes less, like it will become less and less. At the first step, it is less than some Fibonacci number times m. Then after one iteration, A modulo B will be less than Fibonacci number n minus 2, and so on and so forth. So like each time it decreases by one index here, and it will finally become 0. And at that moment, you could see that the number of iterations is how large the Fibonacci number were. But like Fibonacci numbers are approximately like something like that. If you know from the course of mathematics, I think on the first year of the university, Fibonacci numbers grows exponentially with some base, and this means that the total number of these Fibonacci numbers to lower down is some logarithm of this strange base. Okay, so this is why the algorithm works in logarithmic time. Okay, good. That is like the brief. I don't give any details. Like you can prove it if you want at some spare time, but the reality is that. The question then is about LCM. That's another thing that is pretty important for us. In the number theory are A and B. This is LCM, or lowest common multiplier. What does it mean? It is the smallest value that is divisible by A and divisible by B at the same time. So it is like, let's consider an example. I don't know, like 6 and 8. Like they're suggest, okay, why wouldn't we take a times b because it is easier to do, like, but it appears that a times b is not the least common multiplier. It is a little bit trickier. So you can see that for 6 and 8, the answer will be 24. Okay, if we, that I will give you the explanation a little bit later, how I did this. But their idea is that for 6 and 8, the lowest is 24, which is not 6 times 8, because 6 times 8 is 48, right? So it is less. Okay, so how it looks like, typically. So there is a main arithmetic theorem, is that you can represent each number as the power of primes, right? So you have p1 e to the power alpha 1, p2 e to the power alpha 2, blah blah, pk e to the power alpha k. And b is the same but different powers. So it is still alpha can be 0, so that you would understand. Alpha can be 0, so like we don't always have to take the prime in the representation. Okay. Great. So we want to find the GCD. So like right now we were talking like a little bit about GCD. How we can represent GCD out of these prime numbers. So GCD, like GCD of A and B is equal to, let's say, P1 times P2 times etc. times Pk. What I should write as the power? So we want like A is divisible by P1 in the power of alpha 1, and B is divisible by P1 in the power of beta 1. So at what the common divisor, like the common divisor of P1 could be in the power here. Okay, any ideas? Like the one in the chat, probably you can tell me. Okay, nobody knows, like no problem. That makes me sad, to be honest. No worries. So if we consider P1 like separately, so you could consider the P1 here and P1 here. So it should divide P1 in the power of beta 1 and P1 in the power of alpha 1. Okay. So and we want to make the highest power possible out of that. So the answer is just minimum of alpha and beta. So just here mean alpha 1 beta 1, mean alpha 2 beta 2, and so on, mean alpha k beta k. Okay, so this is how their GCD really looks like in their representation of the primes. Okay, the next question. What is the LCM? So it is still represented as the primes. Still represented with the same set of primes, but the powers here are a little bit different. So we want to find the lowest common multiplier. And if we consider separately each prime number, so this power should be divisible by this one and this one. Okay? For P2 it is the same, this power should be divisible by this one and this one. So what will be their power here for lowest common multiplier. I think this should help you. Like this is minimum, and we take the minimum out of them, so it is divisible by. So like that, like this one. This one will be similar to that, but other function. Yeah, Lizzie, yeah, that's exactly what I'm trying to prove here. Yeah. Right, I'm trying to explain why it is this algorithm is so simple. Okay, any ideas? No? Yeah, not very great, but still. The idea is that it should be maximum out of this two. So it is maximum of alpha 1 beta 1, maximum of alpha 2 beta 2, and so on. So instead of minimum here, you have maximum here because it has to be divisible by this power and this power. Okay. And there, like afterwards, when you can look at that, it appears to be quite simple to see the following equality. Is that A times B is the multiplication of GCD and LCM. Because as if you can see here, if alpha 1 is less than beta 1, then this power will be alpha 1, this power will be beta 1, and vice versa. So you took exactly each, like out of two powers, both of them are presented in GCD and LSM. So this is like that, and then the algorithm for LCM becomes quite simple. LCM A and B, it is return A divided by GCD AB multiplied by B. So why I did this in this manner? So like typically the simplest way to write this, it is this one. So A times B divided by GCD. Unfortunately, this can get sometimes integer overflow. Like you know that their answer lies in their integer, but it can be very, very large. If you do that, A and B can come to the integer overflow. So instead of that, you know that A is divisible by GCD. So you just divide A by GCD and multiply by B afterwards. This will give you like no problems with overflow here. Okay. Good. Now we are coming to one of the hardest parts of this lecture. I will explain how to do extended Euclid algorithm. It will be a little bit tricky. So this was a Euclid algorithm that finds GCD, the Euclid, and this one is extended. So you're still given two numbers, and their idea is to find such x which is x and y, so that ax plus by equals to d, which is a common divisor. The idea is quite simple. So we know our GCD algorithm that it works So like that, so it is A equals to P1B plus Q1, then Q, then B equals to B2 Q1 plus Q2, then Q1 equals blah 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 and so on. So at the same moment, so consider something in the middle here, so Qi equals to Pi plus 2, Qi plus 1 plus Qi plus 2. So this looks like that. Let us maintain the following thing through the whole algorithm. Let us maintain for each element its representation in A and B. So this one at the beginning was A times 1 plus B times 0. This one is A times 0 plus B times 1. So and we know from here that Qi plus 1 is, I don't know, x I plus 1 A times xi plus 1 plus B times y plus 1. And this one is A xi plus B yi. So you know the representation of each number in x in this form. So then, obviously, after this representation, you can get the representation for Qi plus 2. Because if you move everything from the right to the left, you'll get exactly like that. So Qi plus 2 equals A times xi minus Pi plus 2 xi plus 1 plus B yi minus P I plus 2 times y plus 1. Okay, so we know how Qi looks like. We know how Qi plus 1 looks like. Then we can get how Qi plus 2 looks like by moving some brackets in there, so let's look like that, because you just go take this and subtract from here. This looks like that. So the algorithm remains quite simple. So you have GCD, you have to calculate GCD, AB, and you pass two arguments like XA and XB. Okay, if B is equal to 0, then I return exactly XA. Because you know B is equal to 0, A is equal to the GCD, then we know how it is represented. So this is XA and XB are the representation of A and B. Sorry. Let's not confuse it. It's a little bit confusing here. XP, XQ, and if Q is equals to 0, then we return XP. This is not the same A and B, because A and B, this is the thing that we pass through our function. So if Q is equal to 0, then this means that the P is GCD, and we know how we represent it. Otherwise, you create a new array X of 2 integers, and you apply this function. So it is XP 0. Oh, sorry. The first, we need to get the multiplier. The multiplier will be X, and this is P divided by Q. So as you can see here, Pi plus 2 is the division of Qi and Qi plus 1. this is the reminder. So we calculate this x, so this is exactly this pi plus 2 here. So, and then you take and x equals to xp of 0 minus x times xq 0 and xp1 minus x times xq1. So this is exactly like that, like the thing here. So it is just the first parameter of x, which is xp0, minus the divider times, oh, there is, sorry, there is too many same variables. So you can see that it is the first representation minus the divisor times the second one, and so on. And then what GCD should I call? What is? Can you tell me what are the parameters of the new GCD? Oh, sorry. Return. What should I pass recursively to GCD? That's the question. So it has four arguments. We know PQ, XP, XQ, and here we know that the next part of the Euclid algorithm is running on the B and the remainder of Q and the remainder of B divided by Q. So what should I call here? Sorry?
Parameters.
What parameter x?
Like you can write m over there in GCD function.
Yeah. So okay, the first parameter, what will be?
M.
M. I think it is M. Okay. Then the second parameter?
X.
X. The second parameter x. Okay. You can see that this is already doesn't match because like x is there, like is an array, and you're passing x as the second parameter, right? So this doesn't work. Okay, let's remember the Euclid algorithm that you probably write up in yours. So like it was PQ, and then it should be Can you tell louder? Sorry, I have not very good ear sight.
Which you call like QP parameters over there.
Okay, so Q. Okay, good. You guessed the first parameter. That's already a good start. Okay. So what in the Euclid algorithm their second parameter? No, M is P divided by Q. It is P divided by Q. So what is the second parameter? You can of course you can look at the algorithm that you wrote down. Okay, so let's try to remember. So in GCD we have GCD AB and we run then GCD B and then what? What was there?
A mod.
Yeah, it was A mod B.
Yes.
So what do you have here?
Q mod.
Yeah. No, not Q, vice versa.
P
It's P mod Q.
P mod Q. Okay, good. So this is exactly the same. We know that P, like the representation of P is hidden in XP. The representation of Q is hidden in XQ. Okay, so what should be the third parameter?
Index Q.
Which one? Index. No. Okay, so what should be here? The first one should be how Q looks like, and the second one how P mod Q looks like. Okay, so which array represents Q? Which array here represents Q? Okay, we're right here. So you know that XP represents XQ, yeah, that's the symbol. Like that's XQ, yeah, exactly. So the Q is represented by XQ, which we're given above. And what represents P modulo Q?
X P mod.
Yeah, but we already calculated it. M is not an array. M is not an array. We want to.
X.
Okay, I don't know why this found so complication. I mean, we have only 3 arrays here. We have XP, XQ, and X. XP represents P. XQ represents Q. So what represents P modulo Q? X. Yeah. And that's how it works. Okay. Okay, this is the, I think this is the hardest moment of the whole today's lecture. So okay. So using this Euclid algorithm, you can find the inverse of their value. I will give a brief explanation. So you want to find a minus 1 mod m. So for that, if a and m are doesn't have the common divisor, so you can using their algorithm that I presented right now. So this is am equals to 1. So it is ax plus my equals to 1. And if you take this modulo m, this will go out, and you will find ax modulo m to 1. So x is exactly the target, because like x is exactly the value that is multiplied by m, a returns 1. So this is the inverse. But I will explain how to do this, I mean, like easier. How to do that easier. Okay. So now I will explain on how we find the power of some value by some model. So we want to have a times p mod q. So we want to calculate this one. The question, how to do it fast? I'll explain right now. So wow, a pq So this is whole implementation. I will explain right now how it works and why it works. So consider P as some binary string. Then their power of A will look like the following. So A, it is like this is 1, 2, 4, 8, 16, 32. So it's 2 in the power of 5. This is the first 0. Then you skip the power of 2. Then you take the power of 3. Then you take the power of 2. Then nothing. And no, something is wrong. Okay, like this. Oh, sorry, I did a huge mistake. Here, yeah, so this is 1, and this is, so a in the power of p is equal to a, and we consider this p as the powers of 2, so it will be 2 in the power of 5 plus 2 in the power of 3 plus 2 in the power of 2 plus 2 in the power of 0. So this is exactly the representation of p in the binary way. Okay? And then I separate them. This will be equal as a 2 in the power of 5, then a 2 in the power of 3, then a 2 in the power of 2, and a in the power of 0. it appears that this is exactly how our algorithm works. So we start from the lowest bit. So we start from the lowest bit from here. So we start with currently currently it is A, and we check if P modulo 2 is equal to 1. Okay? P modulo 2 is equal to 1. Like we are kind of going from right to the left over the bits. Okay? So we just go from there. And at the beginning it is A, and P modulo 2 is equal to 1. So we multiply answer by 8. So ans equals A in the power of 0, in the power of 1, like in the power of 2 in the power of 0. Then what's happening? Then we take A and squared it. We have A in the power of 2. And we come to the next digit of P. So we were here, and now we came for the second digit. We can see P is divisible by 2 at that time because like the last bit is 0. Then we don't change A, but we multiply, like we take the square of A again. So it is, except it was A in the power of 2, then it becomes A in the power of 2 in the power of 2. So it is A 2 in the power of 2. Okay, we already got this digit, digit. Then we divided P by 2, so we are looking at the latest digit here. And what is it? It is 1. So we have to multiply answer by the current A. So it was A in the power 2, 0, and it will become A in the power 2 in the power 2. And then we square it with the square, and we will get 2 in the power of 3 here. So currently it is that. Okay, we continue. So we already out of that. And we see that P modulo 2 is 1. So we have to multiply answer by the current value of A. So it is A in the power 2 in the power 3. And again, we take the squared part here, and we get A in the power 2 power 4. Again, so like that's, if we close that, then we see that the latest digit is 0, so it doesn't fall in this case. Then we go to square it again. We square it, and we get A in the power 2, 5. And finally, we are at the latest digit here, and we check, okay, it is 0, then we should multiply answer by the current value, which will be A 2 in the power of 5, and finally we finish because P becomes 0. So as you can see, the answer is exactly what we expected here. So this is the whole algorithm, how we take the power of something. Any ideas what is the complexity of this algorithm? What do you think? ideas?
Big of n.
What?
Big of n.
Yeah. Not n, but p.
Okay.
Yeah.
Big.
This is depending on the power of p because you go over all the bits, so this is logarithmic p. Yeah. If we come further, so if q is the prime number, it is known that a in the power of q minus 1 modulo q equals to 1. This is their a little Fermat's theorem. I think I will not go into prove it here. It's quite easy to prove, but still, this is out of scope. Okay, so if q is the prime number, then this holds. This part holds. Then I want to find an inverse of a. I want to find an inverse, like as we did with extended algorithm. Like I want to find x such that this happens. I want to find this x. So given this and this, can I find x? Okay, let me save the time. It will be a in the power q minus 2. Okay? Because if you multiply a in the power q minus 2 by a, you get a in the power q minus 1 and you get 1 here. So you can calculate their inverse in logarithmic time because you just have to take the power of q minus 2. Suppose that we have a recurrent relation. Right now, we just know how to do the binary, like this is named like binary power algorithm, as far as I remember. Because you always work in the powers of 2, so this is why it's binary power. The question is the following. So suppose we have a recurrence relation, something like that. N equals to a n minus 1 x n minus 1 plus n minus 2 x b2 x n minus 2 plus k x minus k. So suppose we're given like this reference relation. For example, for Fibonacci numbers, it will be Fibonacci number equals 1 times f n minus 1 plus 1 times f n minus 2. So this is the reference relation here. And we want to find x, which is very, very far away. Not the number that is very, very far away. So it appears we can do this in kind of logarithmic time also, with the binary power. The idea is pretty simple. So we want to find the matrix. We have here x n minus 1, x n minus 2, x n minus k. You want to find a matrix that multiplying by this gives xn minus 1, and etc. xn minus k plus 1. So kind of we have xn minus 1, xn minus k, and then we make a step by multiplying the matrix, and we get the next batch of k elements. Like, we shift it a little bit by xn. So can you tell me what this matrix should be? How it looks like? So we have this line here, and we want to multiply this line by this vector and get xn. And you have this relation.
xn plus 1.
No, xn plus 1 is not here yet. It will be on the next step. So again, you want to multiply this row by this column and get xn. And you know this one. This one. Somebody in the Zoom can do that. So guys, any ideas? Like how it looks like? Possibly I have to remind how the multiplication of matrices work on the vector. So you take this element, multiply by this one. Then you take this element, multiply by this one. And so on, and the final element multiply by this one. So as you can see here, this is exactly the multiplication of the column on the row. What will be here? Yeah, the first one will be A1. Yeah, exactly. You multiply A1 by then
A2.
yes, and so on, and it will be A8. Yeah. So nothing hard here. Like my questions are entirely stupid. Like that's you multiply this row by this one. Okay. Then you have to find the row, such row, that multiplying by this row it will give us xn minus 1.
E2. We'll start from E2.
Not necessarily. That's not a good idea because we don't have xn minus k minus 1 here. Like, we already forgot about it. Like, kind of. You can see. So we want to find x. We want to have xn minus 1 here, and we have xn minus 1 here. So it's just kind of to cut this element out of the whole column. How we can cut this element? Okay, quick like kind of the hint. Should be this row contains only ones and zeros. Sorry?
0.
At the first one is 0. Okay, suppose the first one is 0. Okay, what next?
1.
1. Okay, then what are the next? Let me give you the hint here. So suppose this is 0 and 1, okay? We take this one. Then how it looks like? It will be 0x n minus 1 plus 1x n minus 2 plus, and there's some questions after. And we want to get x n minus 1 here. Zoom. Is there somebody in the Zoom? It seems there is nobody in the Zoom. Okay. The answer is again very stupid, so I don't know why there is there. So Polish probably you don't understand my questions, that's the reason. So their answer is 1 0 0 0. Why so? If you multiply this row by this column, you will have 1 here, 0 0 0 0 0 0 0. So you get exactly x n minus 1, okay? Then, the next stupid question. What should be the third row? We want to have here x
n minus 1.
and x n minus 2 already here.
0 1.
Yeah, it should be 0 1, 0 and etc. And so on and so forth. So like it is 1 here until the end. Okay, then how we can create their very, very distant element from here. You can see that you have the special matrix that multiplying the vector can give you the next step of their recurrence. So the idea is that we can just say something like that. This matrix in some power, in their necessary power, of course. Like how many times you should apply this matrix to get the desired number. So you just multiply, and it should be in the large power here. And then to make it faster, you use for the multiplication of the matrices this algorithm because it works in logarithmic time. So you just have to multiply this matrix logarithmic time by itself. So you just like here like this multiplication is not necessarily to be multiplication of the integers. It can be the multiplication of matrices. Okay. Okay, can you give me the matrix for Fibonacci numbers? So you can look on that matrix, how we did in the general case, and then create their matrix for Fibonacci numbers. Yeah, let's start from the simplest question. What is the dimensions of this matrix? How large it should be? Two. Yeah, okay, good. Two. Okay, we have matrix of size 2. Here, here, here. Okay, how should I fill it? You can see here. Here, what?
Yes.
What is here?
Once.
1. Okay, here. 1. Here. 1. Okay, here.
Once.
Also 1.
Yes. 1 0 0 once.
Where is 0? Here 0?
Yes.
Like that?
0.
Here 0.
0 1 sir. 2 second row first column. 0
That? Or here is 1. Like this.
Above will be 1, I guess.
1 1 1 0
and then 1 0.
Yeah, should be like that. It should be
1 0.
yeah. So okay, as you can see here, like A's are 1s because this is 1 here. So like the first row is 1s,
0 0.
and the second row is 1 because like you can split. Okay, so you have to leave like the previous Fibonacci number and cut out the last consequence. So this is the sum of 2 and then. No. So to calculate the very large Fibonacci number, you can take this matrix in their large power and like get it. Simply. Okay. this. It can help you to find a lot of prime numbers at the same time. And how it looks like in real life. So we take the smallest prime number, which is 2, and then tries to stroke all the elements that are divisible by 2. So we stroke 4, 6, 8, 10, 12. Okay. And we take it as a number. Like take the next element, which is not stroked out. This is 3. So we take 3. We throw away everything that is divisible by 3 right now. So it is 6, 9, and 12 again. Then we take 4 is stroked out. We take 5. 5, like kill 10, and so on. So like that, then 7, then 11, and so on. So this algorithm just goes from left to right and try to stroke out all the elements that are divisible, and at the end you will get all prime numbers. Like the ones that are not stroked out are prime. Because why so? Because there is nothing smaller than them. Then like if p was divisible by something, that p should have been stroked out. The algorithm is pretty easy to write, so we go for I equals 2 times 2n. Then if not prime I, then continue. Otherwise, we go for j I times I and j less than n, j equals I times j plus I. Then we set prime and j. So the algorithm is pretty simple. You just go over all the elements starting from 2 to n. If it is not prime, so I mean this is stroked out, then we do nothing. And if it is prime, then we go by all the elements with the step I. So you started with I times I, and you go j plus I each time. You like increment j by I each time. So kind of, and you stroke out all the elements. So like, typically you can even, to simplify this, you start from 2 times I and so on. Okay, that's the whole algorithm. That's it. The complexity of this algorithm is a little tricky because like the straightforward complexity could give you like 1/2. So you just you took 2 and passed through all the elements before n. Then it is 1/3. You take 3 and like stroke everything. Sorry, and like that. You stroke everything with the step 3, then n divided by 5, then n divided by 7, then n divided by 11, and so on. So this is how the running time looks like, and it appears to be of this complexity. So their inverse of their prime numbers are log n. Okay. Another still interesting question. Suppose we have like we know all of their elements. No, we want to factor all their elements from 1 to n. We want to factor them. So like kind of you just ask any number m, and it gives you its factorization pretty fast in the prime numbers, like that we see that we saw previously with GCD. We want to like find all the divisors and etc. Blah blah blah. Okay. We know the algorithm that finds for the element m all the its factorization in square root of m, right? We started with this algorithm at the beginning, and it worked in square root of m time to factor it. So it's pretty slow. If we try to do that for each element from 1 to m, then the complexity will be m square root of m. So this is not exactly that what we really want. We want to be faster. So the idea is pretty simple. Let's decide that we store not only prime, but some divisor of the value. So if div I not equals to -1, sorry, not equal to I, then we go over everything and we set that div j equals I. So you just set this array div will give you there some prime number on which it is divisible by. So if it is equal to I, then it is the prime number. Otherwise, we go over everything and set the divisor to this prime, to some prime number. Okay, so given this array, we can restore the factorization because you are given x, and then while x bigger than 1, you take divisor div x. So this is some divisor of x, and then we continue with x divided by this d, and so on. So kind of while it's not 1, so there are no divisors at all, we took there some prime divisor of x, and then divided by this divisor. And by that you can print, for example, print here or something like that, print d that this is the prime divisor. That is how you do the factorization generally on the prime numbers. This was Eratosthenes. And then I think the final topic for today will be Chinese remainder theorem. that's an interesting task in the sense that you are given the reminders by modulo. So you know that A is the modulo of A by M1 is N1, and so for k different modulos. And we know that all these modulos are with GCD1 up. And you want to find A. So the question, so you're given the reminders, you're given you're given modulus, and you want to find A. Why this problem is necessary? For example, it's typically easier to calculate for some problem there by some modulo, and then like by several modulo. You run your program for several modulus, and you get several answers, and then you just using that you will restore the real value. If you take enough modulus, like some prime modulus, you can easily restore the real answer from that. Okay. So we will present it. We will present A in an interesting form. That it will be N1 plus. Sorry, let it be P1, P2 times A1. Sorry, not A1, N1 plus P3 times N1 and 2 plus, and so on. So the idea is the following: like, you multiply n like one by one until the end, and then the question is to find this piece here. Okay, can you tell me what should be P1? Okay, any ideas? Everything to the right is divisible by n1. Oh, sorry. Oh, yeah. I did a mistake. This is not n. This is m here. This is a modulus. This is a modulus here. So you want this by modulo m1 to equal n1. So what is p1? Like, you know that this is divisible by m1, this is divisible by m1, and so on. The only thing that is not divisible by m1 is p1. So what p1 is? Seems everybody already tired. So P1 is N1. It's simply N1. Because you want this to be N1, so P1 is N1. Then you want P1 plus P2 times M1 modulo M2 will be M2. Because like we can throw away the whole tail for everything because they're divisible by m2. And from that, you could see that P2 is n2 minus P1 times m2 in the power minus 1. Like, this is the inverse. This is exactly what we did at the beginning. We found the inverse of the integer there. Okay, then P1 plus P2 m2 times m1 plus p3 times m2 modulo m3. Oh, sorry. M1 here. 3. Modulo p3 is n3. Then p3 is equal to n3 minus p1 minus p2 m1 multiplied by p3 in the power m. Sorry, p. Okay, I made a mistake here, so it is m1, p2, m2, in the power minus 1. Okay? And so forth and so on. You just have to maintain this thing and recalculate, like by taking to the other side. You just compare by modulo. In the problems today, you will have to do the simpler version. There are only two different modulus, and then you have to find nothing. Okay. Are there any questions? Yet. How much here? 1 hour and a half has passed, so I think I was too fast, it seems. Okay, let me then possibly to finish with the little Fermat theorem. How to prove it? So you want to prove it that a p minus 1 modulo p equals to 1. That's you want to prove. There it is the following. Let's take all the elements from 1 to p minus 1. Okay, the interesting fact is that if you multiply all the elements by a, this set is also will be equal to the set p minus 1. It's just some permutation of the elements. So if you multiply each element by a, then it becomes like that. Okay, so if the sets are the same, then we can take a1 times a2 and etc. a minus 1, which modulo p will equal to 1 times p minus 1. You just can stroke out everything on the left and right, which is the same, and then you will be left with a p minus 1 modulo p, which is 1. Okay, this is the thing that works with the prime numbers. But what if we have not the prime number, but some different number? It appears that there is an updated version of little Fermat theorem. Is that a phi of n in the power of n in the power of phi of n modulo n is equal to 1. So what is phi of n? Phi of n is the number of elements that are prime with n. So for example, if you take 1 p minus 1, phi of p will be p minus 1 because all these elements doesn't have any divisor, any common divisor with p. That is why like phi of pi is pi minus 1, and this is exactly like this theorem becomes exactly as little Fermat theorem. So for example, for 6 or for 12, I don't know, for 12, what are there? So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which are smaller than 12. So 2 is not good because 12 is also divisible by 2. 3 doesn't work because it is also have the same divisor. 4 have the same divisor 2. 5 is good for us. 6 have the same divisor with 12. 8, 7 has nothing. 8 has the same divisor with 12. 9 have the same divisor with 12. 3. 10 has the same divisors with 12, which is 2. Like that. And at the end, you got 3. Just like 5, 7, and 11. Like it is proven exactly in the same manner as the little Fermat theorem, but the problem, like, with the only difference is that not all the elements before n minus 1 multiplied by a can come to this state, because some of them has common divisors with n, and multiplication by a doesn't move exactly. There is no bijection between the two sets. Okay. How to calculate this function? This function is named, like I named it earlier function. This is in their literature. It's named Tottian function. It appears to be multiplicative. So if you have p1 in the power of alpha 1, like pk in the power alpha k, it is equal to phi, like multiplication of this. Like this is multiplicative function, then you can open the brackets, and it appears that phi for p1 for p in the power alpha equals to p minus 1 times p alpha. What does it mean? It means that for p in the power of alpha, each, like the only divisor that it has is p, then each pith element are not good for us. So like p, 2p, 3p, 4p, 5p, and etc. They do not satisfy the Tottian function, and that is why you have here p minus 1. So and by that, when you have the Tottian function, like let's explain how to calculate it. So it's pretty simple. It's almost like the factorization of n. So we go d equals to 2 while n is bigger than 1. Do if n is divisible by d, is not divisible by d, then we continue. Otherwise, we do the following. So we have answer phi, which is n to start. And we just say phi equals n times d minus 1 divided by d. And then n of d equals to 0, we divide n by d. Why it works? So we know that n is the multiplication of prime numbers, as we know from their arithmetic theorem. Like, what is the difference between phi of, so yeah, so phi p1 alpha 1 pk alpha k is equal to p1 minus 1 p1 p1 alpha 1 minus 1 times p2 minus 1 plus p2 in the power of 2 minus 1 and so on. So the only difference between n, which is n here, the n and phi of n is that for each prime number you should divide by the prime number and multiply by the prime number minus 1. So the only change that is happening between n and the tangent function. So this is exactly what we're doing here. We come plus here. So we increment d. We check that it is divisible or not. If it's not divisible, then there is no problem. Then we know that d is the prime number. We multiply. Too many mistakes. We multiply phi by d minus 1 divided by d. Exactly as exactly we want to divide by p1 and multiply by p1 minus 1. You multiply by that, and then you divide on d as much as I want, because I only care about prime numbers. And if I take this all the d's away, then this is exactly prime. This will be exactly the prime number. So that's it. That's how to calculate tangent function, and it will help you to get the inverse one, because the inverse one will be a minus 1 by modulo n is a phi of n minus 1. Exactly as with the prime number, we have p minus 2. Here we have phi of n minus 1. Okay, I think that is it for today. Are there any questions? Okay. In Zoom, are there questions in Zoom? Okay, there are no questions. Then we stop the lecture for today, and we will start their practice at. Okay, yeah. So we stop the lecture and we start the